Want to talk about analytic. Today, I want to talk about analytic strategies for the OAI data. Let's see, I gotta say being recorded, okay. So here's my outline. I'll start off with an introduction and some examples, and talk about some sort of general considerations that I always go through when I'm thinking about analyzing data from OAI. And a key component of dealing with this data is that almost always you have to deal with accommodating correlations, either longitudinally over time between these or regions within these. And that's important to get the proper statistical analysis. All right, so when I think about analyzing a data set, I always start by thinking about the nature of the outcome variable. Is it a binary outcome variable? In which case I might be guided to using something like logistic regression, like presence of osteophytes. And then I would characterize the associations using things like odds ratios or areas under the ROC curve. If I have a numeric outcome, I'm typically going to be thinking of things like linear regression. So things like WOMAC pain, I might treat as just numeric. And I'd fit linear regression type models. But you can also have other types of models, like time to event models, time until knee replacement, for example, that you would handle with a Cox model or a pooled logistic regression. And somewhat less commonly, you might encounter count outcomes, in which case I might use Poisson regression. And of course, any of these methods that you're going to use need to be modified to be able to accommodate cluster data or repeated measures or longitudinal measures over time. So let me just think of some examples and walk through, what sort of considerations we need to incorporate. So for example, suppose quality of life as measured by the Q scale, is that related to somebody's body mass index at baseline? That's just a cross-sectional analysis. There's nothing longitudinal or clustered about it. Example two, is the difference between men and women in the WOMAC pain score the same for those with and without symptomatic knee osteoarthritis at baseline? That's at baseline, so it's not longitudinal over time, but it's still clustered because we've got a WOMAC pain score for each knee for each person. Here's another example of a clustered data analysis, is the presence of osteophytes at baseline predicted by knee pain. Again, we've got measurements that are separate for each knee. A lot of times people want to use the OAI data to answer questions about changes over time. One of the strengths of the data set is the long longitudinal follow-up for participants. For example, is the 18-month change in WOMAC pain score the same or different for those with symptomatic knee OA at baseline? So going back to example one, is boost quality of life related to baseline BMI? I might start by looking at something graphical like a scatter plot, and we see monotonically decreasing relationship of quality of life with baseline BMI. I would just handle this with linear regression. It's not clustered data, and we might get a regression coefficient. The coefficient is -1 with a standard error of 0.09 and some very tiny p-value. This is just a standard linear regression problem, and there's no clustered or longitudinal data here. Very simple to analyze. All right, but what happens when we do have analyses or data sets where we have to accommodate the clustering or the repeated measures? If we don't use specific analysis methods that can incorporate this correlation, standard errors, p-values, and confidence intervals can be incorrect, sometimes grossly so. And I'll show you some examples in a minute. And unfortunately, it's not possible to predict. Okay, some people might like to say something, well, I'm just doing a linear regression, it's clustered data, this is probably conservative or it's liberal. It's not possible to predict which way the proper analysis will go compared to a simplistic analysis that ignores the correlations or the longitudinal nature of the data. All right, so to give you a little bit of intuition, though, for a between person predictor, so say body mass index, the proper clustered data outcome measured on two knees analysis will usually have larger standard errors than a simplistic analysis. The intuition there is that between person predictors, an analysis that assumes the needs are independent will overrepresent the information content. Each knee does not contribute an independent and new piece of information as if it was a knee measured on a new person. There's some redundancy of the information there. On the other hand, if we're looking at a within person predictor, like a knee specific predictor, like the WOMAC knee pain for each knee as the predictor, the proper clustered data analysis method will usually have smaller standard errors. And the intuition there is that using each person as their own control increases efficiency. Looking within a person at differences between the knees is typically more precise than if you collected the information on different people's knees. All right, here's an example. This is going back to example 2. Is there a sex by baseline symptomatic osteoarthritis interaction for the WOMAC pain score? So if we're comparing men and women as to what their WOMAC pain scores when they do or don't have knee arthritis, are the differences the same? So if I'm looking here at the bottom part of this slide, for people with no knee OA, males and females have very similar average pain scores, difference is 0.05. But for people with knee OA, women have a higher pain score, and maybe that's statistically significant. If we incorrectly assume independence, the estimated difference, it's really just the 0.91 subtract off the 0.05, has a p-value of 0.001. If we do the proper analysis accounting for the correlation, same estimate, different standard error, and we now get a p-value that's an order of magnitude bigger. Qualitatively, they're both statistically significant, but it's easy to envision situations that where the case is a little more borderline when one would be fairly highly statistically significant and the other one wouldn't be. But even in this case, of course, the p-values are quite different. All right, so when you analyze the methods for accommodating cluster data or longitudinal data or data on change or repeated measures are all the same. They're all methods that accommodate the correlation between the data, whether it's due to clustering, whether it's due to longitudinal changes over time, or whether it's due to repeated measures. And there are two primary approaches, and those are what are called mixed models or generalized estimating equations. The names for both are a little esoteric, but not really to worry about. These are commonly available in all the major packages. In SAS, mixed models are proc mixed, NL mixed, and GLIM mixed routines. In Stata, it's mixed, MEGLM, mixed effects generalized linear models, MELOGIT for binary outcomes. In R, Lemur, Gleamer, and NLME. And the generalized estimating equations approaches in SAS, it's called PROC-GEE. In Stata, it's called XGGEE. And in R, there are two major packages, GEE-PAC and GLM-GE. Slightly prefer the second one, but both are very reasonable packages. All right, so what would we want out of a method for dealing with longitudinal or cluster data? Sorry, a little sidetrack here. Longitudinal or clustering is only an issue when that clustering or longitudinal nature of the data set is for the outcome variable. It doesn't really matter if it's for the predictor. For example, suppose you're interested in whether days missed from work is predicted by knee pain. So days missed from work is at the person level. And if we're just doing this at, say, the baseline, we only have one measurement for each person. Even though the predictor, knee pain, is clustered, it's measured on each knee. So this does not really have repeated measures on the outcome. And we can deal with this with the standard statistical methods. So we can accommodate this either by including both the left and right knee predictors as predictors in the model, or by calculating some summary measure. For example, average knee pain. And if we're worried about, what if somebody has asymmetric knee pain, maybe that does something. You could have two predictors, one being the average and the other being the difference between the two. All right, so what would we want out of an analysis method to accommodate clustered or longitudinal data? We'd want it to be able to accommodate a variety of different outcome types, key ones being binary or numeric. We'd want it to be able to accommodate clustering by knee, person, longitudinal over time, perhaps even different regions of interest within a knee. Um, and we would not necessarily want to spend a lot of time modeling the correlation. Usually the correlation is sort of a nuisance factor. We need to accommodate it, but we're not really that curious about it. Um, I'll talk about the differences in the methods in a second, but I would say, in 95% of the examples I run across, people are mostly interested in the associations. The correlation needs to be accommodated for the reasons that I noted, and I'll mention in a couple of other examples, but not of primary interest. So often it's nice not to be able to have to spend a lot of time modeling the correlation. So that leads me to recommending as sort of a base analysis strategy, generalized estimating equations. It works with many different types of outcomes. Um, it utilizes, and it's important to turn on, for example, in Stata, it's not the default. So you want to turn on this robust variance estimate. It obviates the need to model correlation structure. So the basic idea is that it uses the empirical results, your data set itself, to estimate and accommodate the correlation structure. So it's not very dependent upon what correlation structure you use as sort of a working model to get your estimates. It works well as long as you don't have too many repeated measures per subject and you have a large number of subjects. So for many analyses in the OAI dataset, you're going to be able to use hundreds, if not thousands of participants. So you probably have a large number of participants, subjects, and not that many observations per person. Even if you use, full longitudinal data and a couple of knees, or even a small number of regions within a knee, it doesn't add up to that many repeated measurements. So this is ideal for analyses that incorporate multiple knees and time periods. It can get less good if you're using just a small subset of the OAI data set and you're using like 10 different time points, two knees, and five regions within a knee. Then you have lots of observations per person. These sort of methods can then work less well. Both these methods, GE or mixed models, can accommodate unbalanced data. Some subjects contribute one knee, while others contribute two, or they don't have all the same amount of data, which is invariable in a data set like this. Okay, one big proviso that might cause you to think about using mixed models instead. Always be wary of the genesis of missing data. If the fact that the data are missing is informative, i.e. those with missing visits are in extreme pain, but you don't get to see them because they missed their visits, then virtually no standard statistical method will get the right answer. With considerable missing data, especially due to dropout, common if you're analyzing later time periods from the Osteoarthritis Initiative, consider using or comparing, GE might be your first analysis, but compare it to a mixed model analysis because mixed modeling accommodates and it is sometimes slightly less biased with informative missing data, or accommodate missing data with something like inverse probability weighting. Here's a reference to that methodology, and or use empirical standard errors with mixed models. So use the mixed models to get your estimates, but then use the data to estimate what the correlation structure might be. All right, here's going back to example 2 and comparing these different analysis methods. Again, is there a sex by baseline symptomatic OA interaction for the WOMAC pain score? Assuming independence, that's incorrect analysis. GE with the robust option turned on, mixed model plain, mixed model with the empirical standard errors turned on. The estimates are all the same. The standard errors vary by a fair amount. You can see the p-value is pretty drastically too small for assuming independence. The GE method, pretty dependable here, and mixed model is a little off maybe because I haven't modeled the correlation structure correctly in this simple mixed model analysis. When I turn on the empirical standard errors, it makes the correction and gets the standard errors probably correct. That was SAS, I'm sorry, SAS GE or GenMod with the repeated option. SAS in mixed, you can turn on the empirical option. In Stata, you can do cluster or cluster robust standard errors added to almost any command, including the mixed model commands. All right, here's another example. Does pain predict presence of osteophytes at baseline? Um, you can fit a logistic regression model that accounts for clustering using GEE and get answers like the odds of an osteophyte increase by 12.5% with each increase in pain score. So you can fit logistic regression type models and accommodate the correlation. As I mentioned earlier, of course, we're going to have interpretations with logistic models that are odds ratios and things like areas of the ROC curve. But you can still do that accounting for clustering by subject. There are a couple of additional considerations to think about when you're analyzing longitudinal data. Namely, you have to include a time variable in your analysis because that's what captures the changes over time. Inclusion of a time or visit interactions with baseline predictors will allow you to say whether or not baseline predictors are associated with change over time. So remember what interactions do. Interactions say, is the effect the same or different depending on another variable? So if we're interested in whether change over time is different, our time variable, like visit, is capturing change over time. And if we want to know if that differs by some baseline characteristic, we need to include an interaction term. It's different if we have a time varying predictor. So MRI findings at sequential visits. We can just include those in the model if we have a variable that changes over time. But if we have something that's fixed, then we include an interaction with time. Another sort of key consideration with longitudinal data is you may want to use lag variables. If you use a predictor that's from a previous visit, that can help you establish either whether it's prognostic and because of time precedence, it may help strengthen the inference of causation. It doesn't prove causation, but we can never basically prove causation from observational studies like OAI, but it can help strengthen that inference a little bit. All right, so here's another example, going back to example 3. Does 18-month change in WOMAC pain depend on baseline symptomatic knee OA? So I would include an interaction term here because it's the baseline symptomatic knee osteoarthritis. Here are the comparisons: independence, GE robust, mixed, with a random effect of person, empirical. So again, the coefficients are all the same. Standard errors differ a bit. Here we do see that we have borderline statistically significant p-values when we do the proper analysis. We have a p-value that's threefold higher when we incorrectly assume independence. So again, emphasizing the point that these proper analyses can be either more liberal or more conservative compared to the naive analysis. You can't predict which direction they're going to go when you do the proper analysis. All right, so what about a lot of times people ask me, can I just analyze change scores? That's an excellent and a simple method when there are only 2 time points, so there's only one change. But it's not as attractive with either multiple time points or imbalanced data. You can get loss of efficiency. Even if you only have 2 time points, you can get small gains in efficiency by including them in one of these methods. And if you do analyze change scores, in some literatures, it's pretty common to analyze change scores and also adjust for the baseline value. I don't recommend that. And that will usually create biased estimates of change. I'll show you in a second how that works out. All right, so here's just a simple data table. Here's the WOMAC knee pain score at baseline and visit 12 months, divided by whether or not they had symptomatic knee OA at baseline. So at baseline, those with symptomatic knee OA, not surprisingly, had much higher pain scores, but they actually dropped a little bit by 12 months, whereas we also see a slightly smaller drop in those who didn't have symptomatic knee OA at baseline. All right, what does a formal analysis of this look like? If I use a longitudinal analysis, the difference in the change baseline to 12 months between the OA and non-OA groups is about 0.27 with a standard error of 0.13, p-value that's just slightly statistically significant, 0.045. If I use a simple change score analysis, I get basically exactly the same answer. If I adjust for the baseline value in addition, it gives a difference of 0.42. And notice, this 0.27, that's basically just the difference in the two changes, which is kind of what we'd expect. The difference in the yes group is a little bit bigger than the difference in the no group by about 0.27. If I adjust for baseline, the estimated difference is 0.42 with a p-value that's about 0. The adjusted analysis is not answering the same question. It's not answering whether the change in time is different between the two groups. So I don't recommend this as a standard analysis. There's an interesting article some years back now by Maria Gleamore, which shows that adjusting change score analyses almost for baseline values almost never answers a reasonable causal question. So you probably don't want to be doing it. All right. That's the end of my presentation. I have a few minutes to be able to answer questions. There's my contact information. And next up in the seminar series is Grace Lowe on June 8th.
Thank you so much, Dr. McCulloch, for that really insightful presentation. And yeah, as you just said, we are now open for Q&A. So if anyone has any questions, feel free to type that into the chat. I have a question for you here. So what is the role of trajectory analyses to identify trajectories that represent data over time versus using a model with repeated measures?
Yeah. So a trajectory analysis, well, I mean, is a broad term. Most trajectory analyses that I know of are actually simple, specific examples of these sort of methods. So typically with trajectory analyses, you're fitting some sort of smooth curve over time. So it's a question of how you treat the time variable or visit. So in the simplest sort of trajectory analyses, you fit like linear and or quadratic curves, usually separately by group, and compare the groups. There are also sort of more exploratory methods of trajectory analysis that may attempt to group people into trajectories. I would call those group-based trajectory analyses. Those are a little bit different because they typically look for latent categories that underlie the groupings. So that may be what you're talking about. But again, the basic statistical methods that underlie those methods are either GEE or mixed model analyses.
Thank you. Oh, we just got another question. Says, thank you for your presentation. For the change analysis with the baseline predictor, is it enough to look at the interaction team, or should we
Sure.
also look at the main effect term?
Yeah. So when you're interested in whether a baseline predictor is associated with change over time, that primary question is answered by the interaction term. So no, you don't need to look at the main effect to answer that question. Of course, almost any estimate in a regression model tells you something. If you've coded your time variable so that time 0 is baseline, then the main effect is the comparison at baseline. So that still might be of interest, but it doesn't answer the question whether the change in over time is related to the baseline predictor.
Another question, are there analytic approaches that we need to consider when combining data from different imaging projects?
Yes. Sometimes the different imaging projects have were conducted with not straightforward, like randomly sampled designs. Sometimes some of the imaging projects, especially early on, when reading the images was much more expensive. Now it's gotten a lot more automated. Were like case control designs, and sometimes that can introduce bias into the analyses. So it's almost always a good idea to do a little bit of descriptive work, perhaps by considering estimates from different subsets of the data, make sure that they're relatively consistent before combining them, and to look out for subsets that might have been conducted with somewhat unusual designs, like, as I said, with a case control or maybe even a case cohort design.
Great. Another question. Amazing presentation. Quick question. In your example, what are the advantages and disadvantages of using right and left knee pain separately as predictors versus using an average pain measure as a predictor? If using separate knees, you are adjusting for pain in each side, how is that considered in the interpretation?
Yeah, so if let's say that knee pain is the primary predictor of interest for your study. So, it's important to think ahead. I mean, why would you want to say left knee pain is predictive of such and such? It would probably not really be a very sensible way to characterize the results. Um, and so I might then gravitate to using something like, okay, average knee pain is probably what's going to be causing people to, I think the example was missing days of work. Um, but you might be able to make an argument that asymmetry in knee pain, having one knee very painful compared to the other knee, might be important as well. So that's why, I might gravitate to doing that sort of a pre-summary of the predictors and put them in the model, checking to make sure, just to make sure that asymmetric knee pain wasn't important. And then I could simplify down to just say, look, we incorporated knee pain in both knees. What we found was that really it was the average knee pain that was important. Here's the interpretation. On the other hand, if you're interested in something like a gait analysis, asymmetric knee pain may be an important driver, in which case that then might be the key predictor of interest.
Thank you. I'm not seeing any more questions, so it's about time to finish up for today anyway. So I want to thank you again so much, Dr. McCulloch, for that excellent presentation and taking time to join us today. And I also want to thank everyone else for joining us. And also, as we wrap up, I want to invite you all to our upcoming webinar, hosted on June 8th with Dr. Grace Lowe, who will be talking about lifetime physical activity data. I'm sending a link in the chat to register for that if you're interested, as well as other links to previous webinars and the post-webinar survey. So yeah, thank you all for your time, and I hope you all have a great rest of your day. Thanks.